And hello, welcome back, OpenFoamers, to this YouTube video presentation. Now, in the last video, we're talking about getting a correlation between some thermophysical properties and temperature. Though I kind of made one mistake, I think. Okay, so if you notice, OpenFoam usually likes to use degrees Kelvin as the main unit of measurement for temperature. But all these correlations are in degrees Celsius, as you can see here. So there is some adjustment we need to make. So yeah, how do I know this? If you take a look at the OpenFoam Thermophysical Guide in the openfoam.org, it says that the temperature limit is usually in Kelvin. So for example, in here, where we have H polynomial, we will have this temperature limit in Kelvin. So we can assume, by and large, the thermophysical properties are usually done in Kelvin, whether it's density or otherwise. Yes, so for example, let's start changing our rho equation of state to fit this. So let's add 273 to our temperature. Okay. Equals this plus 273.15 or 16, yeah, whichever. This is close enough. That's as exact as I think it's okay to get. Okay, so for example, this, and then we go to data, and okay, format. Yes, okay, this will do. I'll shift this from this temperature in degrees C, I'll shift it to Kelvin. Okay, why isn't that working? Okay, maybe I should do a select data, chart design, select data, and I'll edit. Then the X values should be here. Alright, okay. Likewise for this, I do a chart design, select data, edit, I have the X values. I'll be this. Okay, so yeah, I'm going to get all these coefficients in. I'm going to zoom in so that's easier for you to see. Okay, so 1363 for density. Okay, 1363 is here. So this is valid from 15 degrees all the way to 405. So that's pretty good. Okay, maybe I'll put a mark there. It says, okay, valid from 15 degrees C to 45 degrees C. Okay, so I will insert this here, first coefficient, then this will be the second coefficient. Second coefficient, third coefficient, and the fourth coefficient is 2 times 10 to the minus 6, or minus 2 times 10 to the minus 6, which is the same. I will keep that. Next, I look at the CP, which is just to the right. First coefficient, 1666.5. Now paste it here. Second, minus 648.79. So that's a minus there. Okay. Third is a plus 0.34. Okay. And next is 6, minus 6 times 10 to the minus 5. So this one changed to 6. Last one is 3 times 10 to the 8, which is the same. I'll just save that. So it's a plus, minus, plus, minus, plus. So it's a plus, minus, and plus. Just want to check the signs. Likewise, plus, minus, minus. So plus, minus, minus. As the signs are correct. Next thing we want to do is for mu, which is the viscosity. Of course, we want to do it in this form, in this seconds, Pascal seconds, so that it's a correct unit. I'm going to insert another scatter plot, and I'm just going to zoom in on the viscosity as is here. Okay, so you can see a very sharp curve. We can do another polynomial fit. So I'm going to insert a trend line, polynomial, and then we can do the same. Okay, display equation at r squared. So polynomial second order is not good enough. We'll probably want to go a little bit more. Okay, so this is our trendline options. We go higher polynomial, higher. So this polynomial order 6 is about the best we can get, the best fit we can get. We can also do logarithmic, which doesn't actually work, so polynomial seems to be the best. Let's try doing a 7th order. Okay, Excel doesn't quite do a good 7th order polynomial, but again, this will have to do for now. It's not quite a perfect fit, but it's the best that Excel can offer. You can do it conveniently. So let's copy and paste these values down. Remember, this is for viscosity, which is mu. Okay, let's just add the note again. I forgot to add the note. Valid from 15C to 405C. I'll write that in. Okay. And I'll delete this and I'll put the first one. Now, second one is this, which is a negative, minus so and so. Third is phi e minus 5. Phi e minus 5. Fourth is a minus 1e minus 7. So minus this much. Fifth is this, 2e minus 10. Minus 10. Sixth coefficient is this much. Minus 1e minus 13. Okay. And last one is phi e minus 17. Of course, you start wondering whether there are more decimal points there, but no matter, they're pretty small, so I mean we can live with some degree of error. You can do less, you'll still be okay. It's 9916, but you can see the design is kind of off. So third order even worse. So minimally, fifth order will still work. Okay, but yeah, this is what we can do for viscosity. Okay, that's about the best we can do. Now last one. All right, better write this down first. Okay. Valid from 15C to 405C. That's where the data is. And of course, this is a curve fit. It's the best curve fit we can get using Excel. Of course, if you have other software, other methods, feel free to use it. But this is a very convenient way to do it, given experimental data put in a table form. Let's do kappa, which is thermal conductivity, and that will wrap up our thermophysical properties for oil. So this is here, and we'll do kappa. And kappa has a very the thermal conductivity has a pretty straight line kind of a relation, so no need to worry too much, it looks like. So let's add trend line. It's a polynomial, and we'll do the same equation and R square value. So it looks like a second order fit is quite enough to do it. So let's see. You can even use a first order, which is a linear thing, and that would work also as well. See, a linear fit would actually work as well, but in just to be, yeah, just so that we can do the second order polynomial, we can leave it as such. So let me do linear. Yeah, I think linear will do it. You can do linear. This is pretty linear as it goes, so I don't want to do too much, overcomplicate things unnecessarily. So again, two coefficients here, 0.1856, right, for the first one. .1856. Secondly, it is 0002. 0.0002. Okay. Okay. All right, that should be it. So let's count the number of coefficients. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Likewise for here, 1, 2, 3, 4, 5, 6, 7, 8. And 4 here, plus 4 zeros, that is 8. Okay, so that's a fair bit of work for just the thermophysical properties if you want to get it as accurate as possible. Now you can do the same thing for, yeah, that's for oil, down-therm in particular. So, so radiation, thermophysical, and turbulence. So now we can move on to a bit of the solids, what do you call it? The solid region, which is a sphere. And right now, our sphere only has a poly mesh entry. So just like how we need to copy some files over, we can actually copy the heater files. Okay, the thermophysical property and radiation properties, we can copy it over. So CPAR heater / radiation properties, and we'll put it in sphere, and we'll put it there. And the other one is thermophysical properties, and we put it in the sphere. Okay, now if you're wondering why, well, we technically should take a look at this first, the simulation type, whether it's laminar or turbulent. But I think we want to deal with turbulent. I'll deal with turbulence maybe in the next iteration of this simulation. So we do something basic and then we just refine it later on. So right now we get the thermophysical properties right first. Then we'll do this later. Of course, you can go and take a look at it. There's no reason not to, but just for the sake of time, I don't want to keep dragging this too long to set up this problem. I just want to quickly see whether a simulation can run, and after that we refine it. Alright, so we are in the sphere. We are in the sphere section, and I want to copy some things over. So let's go to OpenFoam Heat Transfer, CHD, hot sphere and oil, constant, and CD, I will take a look at the oil. because these are the properties where we have the polynomial fit. This is a very useful entry. Okay, so let's take a look at the thermophysical properties as well for sphere. And I want to use a copper sphere. Okay, copper sphere. So this is the thermal conductivity of copper. Okay, ranging from 200 Kelvin all the way to 1200. So you can see the thermal conductivity doesn't really change too much. It can almost look like a linear fit. And likewise for the heat capacity, which is here, doesn't really change much. It increases over several hundreds of degrees, but other than that, should be okay. So what's the temperature range we are looking at? Okay, so in Kelvin, it's from 288 to 678. Okay, 288 to 678. So this is 200 to 600, which is a fair, roughly fair match. I think, yeah, we can actually incorporate all the data in. I mean, why not? This one, we can incorporate maybe from 250 onwards. Yeah, 250 onwards, because there's nothing quite at 288. So I think 250 is enough. We don't need to go to cryogenic temperatures over here, so let's not bother. The simulation isn't going to do that. So 250 all the way to maybe 600, or about 600 will do. And the pressure measurement, I'm not going to care too much. So I'm going to copy this. I'm going to paste it, and I'm going to do the same things exactly that what we have done with copper. I mean the oil. So I'm going to paste text, temperature Kelvin. I'm going to get rid of this. And this is the CP. Okay, J per kg, CP, joules per kg per Kelvin. Okay. Now, this one I'll put a link again in the description. Okay, this is thermal conductivity. Okay, which we also need to copy over. Thankfully, this is already in table form, which is very convenient for us. Okay, so it's I think we just do 250 onwards. Maybe 200 is too much. Yeah, I know I said why not do 200 for the temperature, but there's really no use here. Okay, so we'll just do 250 all the way up to 600. Okay, so I just do a temperature, and this is a thermal conductivity. Okay, and what's the units? We always need to be careful. Watts per meter Kelvin. You can see, of course, it lowers down to low temperature. The thermal conductivity increases like crazy because there's a superconducting, almost superconducting like properties. Okay, so watts per meter per Kelvin. Okay, so it's a capital W. And what is this? The density. Density is 896 per centimeter cube. We can assume constant because this isn't exactly a liquid, so it doesn't expand as much. Yes, it will expand, but we can just assume constant within this temperature range. Shouldn't be too much of an issue, right? I mean, after all, what it really affects is the alpha, which is the thermal diffusivity, and that's what's most important. Okay, so we have equation of state. We still need the molar weight of copper. So let's go to copper molar weight. Okay, so 63.546. I mean, this is a Google, you can just Wikipedia it, but I'm just going to use this one. 63.546. No, that's the isotope. Okay, 63.546, or maybe it's some other isotopes as well, but anyway, that's the atomic weight. So let's key that in. So 63.546. We'll just key in the relevant data here. So transport, kappa. Kappa is I think thermal conductivity. So yeah, so where is the transport? This is a constant ISO. So anyway, there should be no kappa. I mean, no, there should be no mu for this, because I mean, it doesn't really make sense for solid to actually have this constant, I mean, viscosity anyway. So I mean, we can try just putting in this polynomial model first. So let's do a polynomial model for transport. Okay, polynomial. Okay, so let's do a polynomial model for transport, and let's figure out what is this thing. Copper. Yeah, what's the polynomial to put in? So let's give it trend line again. At trend line. Okay, a linear trend line. Okay, I think I'll just move this here. Set equation and r squared. It's much easier to do. Okay, so it does fit linearly. It's a very good fit, but I just want it a little bit better. 993. No, that doesn't look good. I think third order polynomial will do. This is as close as we get. Okay, I mean, a linear model would do fine as well, but I'll just stick with this. So thermal conductivity. All right, let's copy the template here. Okay, and I'm going to paste it over here. Insert and paste, and I'm going to delete the old one. Let's enter the, and next let's enter the temperature validity range. This is from, let's convert this to Celsius. So 250 equals this minus 273.1. Okay, just 273. So minus 23 all the way up to 327. Okay, so this is the valid temperature range. Minus 23. Okay, minus 23 to 327. Okay, so write it in and save. Okay, so mu coefficient, we just leave it as 0 all the way. So 1, oops. So 1, 2, 3, 4, 5, 6, 7. So that's 8 zeros there, leaving the mu as 0, basically. Now the important thing is kappa. Kappa, which is the thermal conductivity, is here. So, okay, so let's put this in. 454.25 minus 0.2913. So minus 0.2913. Okay, next is plus 0.0005. Okay, so next plus 0.0005, and next is 3 times 10 to the minus 7. It's a minus 3 times 10 to the minus 7. Okay, so that's the transport done. And the thermodynamics model, we can copy the template here. Okay, and I'll go and paste it here. Okay, undo that. Undo that. Okay, so yeah, anyway, species, transport, thermodynamics. So I'm just going to insert and paste. Okay, much better. Okay, so where's the validity range? Minus 23. It's 23 all the way to 327. Write it in. And just leave it as it is. I mean, it would be nice if I can put all the comments up there, but I'm not going to bother too much. Okay, so all comments like before all this. And technically it should, just for, you know, keeping things tidy, but I'll just keep it as it is. So this is scatter plot for CP, and we can just do one for copper. Okay, again we insert trend line, add trend line, polynomial, and display equation and R square value. So this is pretty close fit. Let's see whether we can improve the R square value. Yep. Maybe order 4 will do, because this shape here, but if you zoom in, I mean, well, this does fit everything well. Okay. Well, this does fit everything well. It kind of looks a bit weird. You see it with the little curvy thing here. So we assume, you know, there is no need to have all these extra curves. So I just put order 4. Order 4 looks about there. I mean, this is always just by inspection. I mean, what I'm doing is by inspection, so it's kind of guesswork what's the data points in between. But without the extra data points, this looks about the best fit we can go. Okay, so alright. CP coefficient, first one. This, second one, 1.492x. Third one, minus 0.00042. Fourth one, 6 times 10 to the minus 6. So this is a plus 6 times 10 to the minus 6. Last one, minus 3 times 10 to the minus 9. Okay. Now last stop is the row, which is for copper. Copper's density, it's where is it? Here. Okay, pure copper has a density of 8.96 gram per cm cube, or 8960 kg per meter cube. So let's write that down. 8960, and just to note, I guess in the mixture, always good to write this is for copper, or you can put pure copper. Okay, so it's a copper sphere, very convenient metal to work with, and this specifically is for dialtherm A. So let's just put dialtherm A, which is a heat transfer fluid. Okay. So that's the thermophysical property for the sphere, and the thermophysical property for the oil. And okay, I'm just going to add this to Git. Thermophysical properties added in Kelvin for polynomial. So please make sure, try not to make my mistake. Get your units right. That's very important. Alright, so thanks for watching. I'll see you guys in the next video, where we will continue working on the case until we have something that's workable and solvable. Thanks for watching.